At the forefront of significant progress in scientific research is the European Organization for Nuclear Research, or CERN, which is renowned for its pivotal role in atomic and material science research. CERN, particularly famous for its large-scale investigations, has recently unveiled a groundbreaking discovery from its Massive Large Hadron Collider, LHC, a finding that could drastically alter our understanding of the universe. Experts are now speculating that these unexpected results might even suggest the existence of alien life in an alternate reality. This revelation has sparked intense debate and excitement within the scientific community. Could this extraordinary discovery reshape how we interpret the universe? And once verified, what new insights could it offer into the very nature of reality itself? Join us as we explore these recent findings and delve into how CERN scientists are breaking their silence on this chilling new discovery that has the potential to change everything we know. CERN, formerly known as the European Organization for Nuclear Research, has been a central player in atomic research since its founding in the 1950s. Over the decades, it has made significant contributions to scientific advancements and has often been in the spotlight for its groundbreaking experiments. However, it has also faced controversy and concern, particularly regarding the potential risks posed by its experiments, such as the creation of black holes or the disruption of the fabric of our universe. One of CERN's most famous and contentious achievements is the development of the Large Hadron Collider, LHC, the world's largest particle accelerator. Launched on September 10, 2008, the LHC continues to operate today and represents the latest phase in CERN's accelerator complex, stretching over 27 kilometers and incorporating a series of advanced superconducting magnets and accelerating devices. With a total cost exceeding $4.5 billion, the LHC is considered a major investment in scientific progress. The machine has led to some of the most significant discoveries of recent years, such as the identification of the Higgs boson and a variety of previously unknown particles. The LHC accelerates particles to near the speed of light, making more than 11,000 laps in its circular tunnel. Using powerful electromagnets, the collider creates magnetic fields nearly 100,000 times stronger than Earth's magnetic field. While many see this as an invaluable tool for exploring the deepest questions of physics, others have raised concerns about the potential effects of such strong magnetic fields on nearby technology, as well as their possible impact on Earth's own magnetic field. Once these particles reach their maximum speeds, multiple times that of light, opposing particle beams collide with immense energy, producing a cascade of other particles. Many of these particles exist for only fractions of a second before decaying, but analyzing the data from these collisions can reveal new and exotic particles. Researchers use highly sensitive detectors placed around the collision zones to capture this data, which results in a staggering amount of information. Over 15 petabytes of raw data from each experiment. Sorting through this vast amount of data requires substantial computational power and time. In 2017, CERN achieved a major milestone by permanently storing more than 200 petabytes of data in its tape libraries. To put that into perspective, 1 petabyte is equivalent to about 250,000 movies. But what are CERN scientists actually looking for in all this data? Recently, they discovered something unusual with a specific type of particle known as the beauty quark. Quarks are the fundamental building blocks of matter, and they come in different varieties, each with distinct properties. One type of quark, the beauty quark, has a very short lifespan, only about 1 in 1.2 trillionths of a second. The LHC's observations revealed that when a beauty quark decays, its decay process doesn't align with predictions from the standard model of particle physics. Instead of the expected decay into lighter particles known as leptons, either electrons or muons, the quark decayed into muons 70% of the time, rather than the anticipated 50-50 split. This anomaly has prompted scientists to consider the possibility that an unknown type of particle or force could be influencing these decays. If this is the case, it could represent a new area of physics, potentially revealing the existence of previously unrecognized particles or forces. Some researchers are even speculating that this could lead to the discovery of a new fundamental force of nature, reshaping our understanding of the physical world. In summary, CERN's recent findings from the LHC have the potential to radically transform our understanding of the universe, suggesting the possibility of new physics beyond the standard model. These discoveries may offer unprecedented insights into the fundamental forces that govern reality itself, and perhaps even provide a glimpse into parallel dimensions or alternate realities. As this research continues, the scientific world remains eager to uncover what secrets lie hidden in the data. The Standard Model of Particle Physics is an incredibly successful framework that describes three of the four fundamental forces in nature: electromagnetic, strong, and weak interactions, along with the particles that make up matter. However, despite its impressive accuracy, the Standard Model is incomplete. It does not account for gravity, nor does it explain dark matter, which constitutes most of the universe's mass. Furthermore, there are recent anomalies in experimental data that suggest there may be phenomena beyond the Standard Model waiting to be discovered. One such anomaly was observed in experiments conducted at the Large Hadron Collider (LHC), which has inspired physicists to consider the possibility of a new force, mediated by a hypothetical particle called the Z-prime. This particle could interact in unusual ways with known particles like electrons and muons, although its exact role remains uncertain. If this new force and its corresponding particle are confirmed, it would represent a breakthrough in our understanding of the universe, potentially helping to solve long-standing mysteries like dark matter and the nature of gravity. The LHC, located at CERN near Geneva, Switzerland, is the largest and most powerful particle accelerator in history. Since its construction between 1998 and 2008, it has been instrumental in probing the fundamental structure of matter. More than 10,000 scientists from around the world have contributed to this effort, which involves smashing high-energy proton and lead ion beams to study the particles produced during these collisions. One of the LHC's major accomplishments was the discovery of the Higgs boson in 2012, a particle that confirmed the existence of the Higgs field, responsible for giving mass to other particles. The discovery of the Higgs boson was a landmark achievement for the Standard Model, but it didn't end the quest for new physics. Scientists continue to look for signs of particles and forces that don't fit neatly within the Standard Model. The LHC is currently in the process of being upgraded, and when this is complete, it will be able to produce even higher energy collisions, allowing for the potential discovery of new particles, including new types of Higgs bosons. One of the LHC's key objectives is to explore these deeper realms of particle physics and answer questions that the Standard Model cannot. If anomalies or unexpected results are detected in future experiments, it could indicate the presence of new physics, perhaps even a unified theory of all four fundamental forces of nature, including gravity. In summary, while the Standard Model has provided an incredibly detailed and accurate description of the fundamental particles and forces that govern the universe, physicists are aware of its limitations. New discoveries, such as the potential existence of new particles like the Z-prime, are pushing the boundaries of our knowledge and could lead to a profound understanding of the mysteries that still remain, such as dark matter and the role of gravity in the cosmos. The Higgs boson is a crucial particle in the Standard Model of particle physics. Without it, the fundamental particles that make up matter wouldn't have mass, meaning there would be no atoms, stars, or life as we know it. This particle's importance led to its popular nickname, the God particle. The term was coined by Nobel Prize-winning physicist Leon Lederman, who, frustrated with the difficulty of detecting the Higgs boson, originally wanted to call it the goddamn particle in his 1990s book. The publisher changed it to the God particle, and the nickname stuck, cemented further by widespread media attention. Scientists continue to study the Higgs boson for two main reasons: to understand how the physical vacuum in which we live came into being, and to explore how this vacuum can remain stable. The Higgs field is unique in that it gives the vacuum a non-zero mean energy, which influences the universe's fundamental forces. By understanding how the Higgs bosons interact with one another, scientists hope to learn how particles acquire their mass. However, the exact reason for the Higgs boson's mass remains unclear, and there are still unresolved issues in the theory. Some quantum fluctuations might destabilize the vacuum, though this would take far longer than the universe's current age. Researchers are also looking for other Higgs-like particles that could help explain the origin of the Higgs boson's mass, potentially leading to new physics. These ongoing investigations fuel the need for more data and access to higher-energy particle colliders. Despite its discovery in 2012, the Higgs boson took decades to find. First proposed in 1964, it was elusive because of its massive and unstable nature. To detect such a particle, researchers needed to create a tremendous amount of energy in a small space using high-energy colliders. Once produced, Higgs bosons decay into other particles almost instantly, making them very difficult to detect. Scientists had to design the most complex detectors ever built and analyze billions of proton collisions to spot the Higgs boson signature. CERN's Large Hadron Collider (LHC) continues to be at the forefront of this research, pushing the boundaries of our understanding. While its discovery of the Higgs boson was a milestone, the LHC is now focused on answering deeper questions in physics. It is capable of recreating conditions similar to those just after the Big Bang by accelerating particles close to the speed of light and colliding them. These high-energy impacts generate a range of subatomic particles that scientists study to better understand the fundamental structure of matter. In the future, the LHC may uncover new particles or forces that could challenge or extend the standard model, potentially opening up new directions for physics. One major area of interest is dark matter, which is thought to account for most of the universe's mass but remains undetected. If the LHC can uncover particles related to dark matter, it could lead to a groundbreaking shift in our understanding of cosmology. Another key area of research is antimatter. The mystery of why the universe is predominantly composed of matter rather than antimatter is one of the biggest unanswered questions in physics, and CERN's experiments could provide the answers. Looking ahead, CERN plans upgrades to the LHC, which will enhance its capabilities and open the door for even more discoveries. These advancements might help scientists answer long-standing questions about gravity, unify the forces of nature, or reveal entirely new aspects of existence. The future of particle physics promises to be just as transformative as the discoveries made so far.